Yeah.
Can you do sound check?
Am I audible? Good morning, everyone. I'm Ibn. Stop. Good morning, everyone. I'm Ibn Kausar, and today I'll be presenting contrastive domain adaptation by minimizing divergence in source target image distributions. In this presentation, I'll be discussing first the background of the domain adaptation problem, why we need it, and some motivations behind it. And I'll be explaining the methods that we use to do the domain adaptation, and I'll discuss the results and summarize the presentation. First of all, in the realm of computer vision and image processing task specific, neural network training is a very common practice. And if you can see whether the task is image classification, semantic segmentation, or object detection, for all of this, we have two big assumptions that are massive level training data, and training data and test data must obey the same distribution. However, in real world scenario, it is expensive to label and curate large scale training data, and it's more likely to see data and test data having different distribution than the training data in the wild. Let's see some examples before moving forward. Here is an example on the website. You can see that on the left side, the model is trained on some annotated data which can recognize humans, and on the right side, it is asked to label or recognize the humans in the unlabeled data. And you can see there might be some problems, that there might be dataset bias and domain shift and distribution shift. So what could be the solution to this problem, so that even though our model is trained on a different data set or different domain, and it can still perform well on an unseen domain or an unseen data set? Can we train a model in such a way so that even the domain shifts or distribution shifts, we can still expect a good result from the training model without recurring extra label data? Yes, we can do domain adaptation in this to solve this problem. Here is an example how it works. We can transfer the knowledge from a source level domain data to an unlabeled target domain. And we have an assumption that the source and target must have different distributions so that we can align them. Here is an example that we have labeled source data. For example, we have a dog image, chair image, and house image. Those are labeled data. And we have same class data. However, these are maybe from different domain or different distribution, and these are unlabeled target data. So we can make a training set out of it and train the model so that it can do unsupervised domain adaptation on the target data without using any target label. And for training, we require labeled source data as shown in this picture. And for target, we do not need the label data, and we can leverage the source domain to learn a model for the target domain. And here is some example where we can apply this idea. It can be dataset to dataset. Let's say a clear cityscape dataset where object recognition can be performed, and we can apply it in a foggy cityscapes. Or we can also have a dataset, let's say have Amazon product data, and we can perform domain adaptation on webcam images or DSLR high quality images. So we can perform domain adaptation from dataset to dataset. And there can be another example where we can use simulated data from the simulated world and train the model in a way so that it can perform well on the real world data. These are two examples of the simulation data, and where we can transfer the knowledge on real world data. There is some research already done on this annotating large-scale target domain, and it can be impractical in industrial scenarios. And prior works have shown that class labels, they can use class labels to learn domain invariant features and perform classifications. And we can use generalized generative adversarial network to align the data distributions. And one more model that has shown promising result in other domains of unsupervised learning, and that is also used in domain adaptation, which is contrastive learning, to align the samples from two different domains using source classes. And in this paper, the paper we are showing here, they use k-means clustering to get the pseudo level on the target level, and then they align that they use those level information to align with the source class levels. And there is one more paper that has shown that KL divergence jointly trained with cross entropy can align source target distributions. However, even though these works showed promising results, there are some limitations. One is that for adversarial networks, they have convergence issues, and this is very important for domain adaptation, because if we do not have a good domain separation between source and target, the model cannot perform well on those class boundaries. So it has shown that adversarial methods have overlapping class boundaries. And also for the contrastive method that is proposed there, Yada et al. Says that clustering on source domain before or during training is suboptimal. And because of that, it might be a problem for them. And also, it is unknown how KL divergence works along with the state-of-the-art representation learning, for example, the contrastive learning again. And therefore, we investigate contrastive learning with KL divergence and show pre-training on source domain before adding the target domain improves source target optimization. Here is our proposed method where we take the source image and we generate two different branches of it. One is the augmented noisy version of the source image, and another one is the original image. And once we have that, we take the target image and we do not add any noise to that. And we pass all these three branches to a feature extractor. For here, we use ResNet feature extractor, and we use the idea of probabilistic method here. And once we have the mu vector and mean vector and covariance metrics, we can generate distribution out of them. So we create distribution from, I'm showing here one example on the top, which is the noisy version. So we take the distribution from the noisy branch and we generate some samples. Once we do this, perform sampling, we get the sampling as ZS prime. We perform the same operations for rest of the two branches, and we get samples for original source data, and we get the samples from target data. Once we have that, all these samples, we can perform our objective functions, which are the contrastive learning, cross entropy, and divergence. Let's check them one by one. So first is the contrastive learning. For contrastive learning, we need two different branches to create positive and negative samples. Therefore, we first take the output of the generate samples and pass it to a projection head, and we pass it to the contrastive learning. And also we take the original image samples and pass it to a projection head. And once we have the output of the projection head, we can generate the positive and negative samples based on the source levels. So we just use the source levels here to generate positive and negative samples. We do not use target levels anywhere here. And for the cross entropy loss, we only use the source original data, not the noisy version. And we train a classifier so that classifier learns the source image classification, and later we use it for the target domain. And for the KL divergence, we take the original source image samples, and we create a single distribution for each sample and pass it to the KL divergence. And also we take the target image samples and generate single distribution out of those. And once we have those distributions, we try to align the source and target distributions using KL divergence. So this architecture summarizes our whole proposed method. And now I'll be discussing how we evaluated our methods. So first, we take 100% training data for the source domain, and we take 80% training data on the target domain. And this target domain data is unlabeled, and the rest of the 20% target domain data is labeled. We use that for the evaluation purposes. However, the training 80% data is totally unlabeled. And once we have that unlabeled training data from the target domain and the source domain data, we train a model, and we take the trained model, we test it on the unseen target domain, and we get the accuracy for that. We repeat all these experiments with different seeds. So we do around total 5 experiments, and we report the average and standard deviation accuracy out of those. For this experiment, we used 2 publicly available data set. One is the Office 31 data set, which has 3 different domains. One is Amazon domain, and there is DS server domain and webcam. Amazon is basically, it has 4,100 images of 31 classes from, Amazon has 2,817 images, and these images are product images from Amazon website. And the DS server image, we have 498 images, and these are high quality, high resolution images. And lastly, for webcam, we have 795 images. These are noisy, low quality image data. And we use another data set, which is MNIST data set, and it has 70,000 images of 10 classes from 6 different domains. Domains are being generated using counterclockwise image. So we take one image from 0-degree rotation, and we rotate them 15-degree, 30-degree, 45-degree, 65-degree, 60-degree, and 75-degree. So we get total 6 domains out of them. And we perform domain adaptation from M0 to each of them. So that's how we get total 6 domains. And each domain comprises exactly 11,666 images. Here is the accuracy score on Office dataset that we have, and we report here again the accuracy score and standard deviation. We can see that we have 2 baseline models with no domain adaptation. First one is only cross entropy, and another one is cross entropy with contrastive learning. You can see the average performance of those methods are not as good as the other methods that has domain adaptation. And our proposed method is that we pre-train the contrastive learning first, and then we perform contrastive learning with cross entropy and KLD to perform domain adaptation. And we can see that on average, we have 68.6% accuracy on that domain on pre-training, then contrastive and C and KLD. Even though contrastive C and KLD showed a good result on D2A domain, DS server to Amazon, and webcam to Amazon data, it is mainly because the DS server domain and the webcam domain does not have enough data, and it has very few data, whereas the Amazon domain has a lot of data. However, we can see that even though it's the contrastive is not showing highest result on that, but contrastive C and KLD still performs well on that as well. And for the baseline existing distribution alignment method, we run 3 experiments with maximum mean discrepancy, expectation risk minimization, and probabilistic expectation risk minimization method. And out of those 3 methods, probabilistic expectation risk minimization method performs better than other 2 methods, which are MMD and ERM. But overall, the result average score is not as good as our proposed method. And next, we have the result on rotated MNIST dataset. Here we can see again the baseline methods that does not have domain adaptation, even though they show good result on low rotation, for example, 15-degree rotation and 30-degree rotation. When the rotation is more than or equal to 45, they do not show as good result as other methods, domain adaptation methods. And we can see that the contrastive and C and KLD, when we have more than 45 or more than 45-degree rotation, it shows better result than the baseline methods that does not have domain adaptation. Even though the C and KLD basic pipeline shows better result on this data set, we assume that this is mainly because this is our easy data set, and for this contrastive-based method are not that suboptimal, but we have seen on the real world data set, which is Office data set, it is better. And on the existing baseline methods like MMD, ERM, and PERM, those methods, PERM again performs better than other two methods, and our method, proposed method, performs surpasses PERM by 27% on average, and this is the result of our proposed methods overall. And for the convergent model convergence, we can see here that the contrastive loss and cross-entropy loss converges early as early as 25 epoch. However, KL divergence takes almost 100 epochs to converge, both for rotated MNIST dataset and office dataset. And this is mainly because in the beginning, the target and source domain data distribution are different. And when we align, when the cross entropy loss and contrastive loss goes down, and we have better learning of the model, the KL divergence loss also converges. To summarize, the proposed method learns to align the shift in image distribution using a novel contrastive learning framework, and it shows self-supervised contrastive learning of source data before fine-tuning for source target distribution adaptation is superior, and it improves classification accuracy by 5.1% to 18.4% than CE only or CE with contrastive learning. And it outperforms state-of-the-art DA methods by domain adaptation methods by 1.7 to 27% across 6 domains. And to conclude, the distribution shifts due to image collected under different imaging conditions may benefit from self-supervised contrastive learning. And in the future, the proposed method may be explored by considering between class alignment objective along with the domain alignment. And we can experiment on more large-scale real-world data set instead of using rotated MNIST, like a more data set like office data set. And these are some references that we have used for this presentation. And if you have any other questions, I'll take them now. Thank you.